Hello everyone and welcome to Learning at Lambert Labs session. Today's presenter is Tom Schaefer, so I will hand over to Tom to get started.
Great, thanks, George. So I am going to be discussing SQL indexes today, and kind of what they're useful for and any benefits they bring. So yeah, get started. So what is an index in SQL? So obviously SQL is used in databases, storing data, and so on. An index is a lookup table that is attached to a table in a database that's used to help retrieve data more efficiently. It's not necessarily integral to the data, although there are examples where it is in some way integral. So in that way, it can be sort of created, removed, modified freely without affecting the data itself. There are two types of indexes. First is a non-clustered index. That's an index that doesn't contain the original data, but it basically contains pointers to the data in the database. And so, yeah, for that reason, you can have multiple indexes, and it can contain, other than just the references to the original data, it can contain extra columns from the data. And you can also get a clustered index, which does contain the original data. And so only one can be created. And so those are kind of, I guess, abstract definitions, but hopefully they'll become more clear as I get into some examples. Yeah, so why would you want an index for your table? Under a standard table or that's not indexed, new rows are just added wherever there's space in no particular order necessarily. And so because of this, if you want to search through your table, you need to check through each row. So let's say you've got a table with 1 billion entries, say 1 billion users or something like that, if you're Facebook or whatever, then if you want to find a user with a certain name, then you need to check through every single row. And so that takes O of n time. And just as a quick recap, for anyone who isn't aware, this just means on the order of n, where n is the number of users. So yeah, so if you've got 1 billion users, you're having to search through 1 billion rows essentially, which again, if you're Facebook or even not necessarily such a big company, then this can become really inefficient. And this is where an index comes in. So as new rows are added to the table, the index is updated, and provided there is a suitable index, which there isn't always necessarily, but in most cases there are, searching can take far less than the O of n time of a non-index table. So often it's O of log n. So again, if you've got 1 billion users, then that is a dramatic speed up. And again, all this O of log n means is, so say if your n is squared, you're squaring the number of users, then the amount of time that it's taking to perform this search is only doubled. So yeah, again, that's really a pretty big efficiency there that you're getting by indexing your tables. So to kind of just go into the implementation of indexes a bit, or well, the most common index, I'm going to talk about tree data structures for a bit. So there are common data structures we might use in, if you're using Python, say you've got lists, which will just be a very simple ordered array of data. So here we've got the numbers from 1 to 11. Again, in Python, you might just draw this as a list of range from 1 to 11, and yeah, this is just essentially a different way of storing that data, where you've got nodes containing the data, and then children from each node. And I'll give some formal definitions, and then I'll kind of come back to this and discuss it in a bit more detail why it's useful. So the first definition is for a binary tree. Again, this is a tree data structure, and it's also a binary tree. And a binary tree is just a tree data structure where each node has at most 2 children, referred to as the left and right children, which this satisfies. We've got a node here, it's got 2 children, so we kind of go down, left child, right child, and then definition further, or sort of above that, is a binary search tree, which is a type of binary tree, except each node has a key whose value is greater than all of the keys in the left subtree, and the key is less than the value of all the keys in the right subtree. So sort of a recursive definition. You can see this one fits as well. 7 is greater than all of the keys in this left subtree and less than all of the keys in this right subtree. So why is it useful to use a tree data structure? Well, again, going back to that example of a list, let's say you had these numbers in a list, they might be in a random order, and you wanted to find, say, the number 5 in your list. You could potentially have to search through your entire list, so look through 11 pieces of data in that list until you find your number. However, here, if you wanted to find the number 5, well, you look at 7, and you know that 5 is less than 7, so you're going to traverse left down the tree. 4, well, 5 is greater than 4, so you go right to the right child, and there you go, you got 5. So rather than potentially having to search through 11, or I guess on average half of 11, so 5.5 pieces of data, here you're only having to look at 3, and at most 4. So yeah, definitely less than the 5.5 on average, and this kind of improvement is far greater on larger data. And so again, going back to the O of n notation, rather than a search being O of n for a list, this is O of log n. And you can go into the proofs of that, but essentially it's because yeah, you're rather than having to traverse for every single thing, you're essentially doing like a binary search. So yeah, implementation, I won't go into too much detail, but just as kind of a high level overview, you've got a node data structure with left, right, and value. And yeah, these are set as none by default, but to then insert data into a tree, you can use this insert function, which then returns the head of the tree. So just to go back, this is called the head of the tree, and these are nodes. Yeah, and again, I won't go too much into this, but if there's no tree, you're just returning that node. If yeah, and then you compare the key. So you either go right or left depending on the key's value, and then you're returning the root or head root, basically the same thing. Yeah, and so here's an example of how you would create that tree that we saw before. You find the head, and then for all of the values, you're just inserting them at the head. Yeah, but one potential issue with binary search trees is that, again, giving the example that we saw before, to go back to it, this is a nicely balanced tree because you don't necessarily have to travel very far to find the data you're looking for. Here is one example, though, which is a valid binary search tree as well, where there's no benefit to a list because there are no left children. You're just having to travel down the right child the whole way, so it's really no better than list, and actually worse than the list because of the overhead with the structure having to have these nodes and so on. So the tree that you use in a SQL index is a B tree, which solves a lot of the problems of binary search trees, such as having this example. It's impossible to have an example like this in a B tree because it's self-balancing, and I'll go into what that means in a minute. But so yeah, it's a generalization of a binary search tree. It's self-balancing, so yeah, you never end up in that kind of scenario. It's always generally sort of, yeah, you never have to travel particularly far, and I'll go into what that means in a moment. And yeah, so it allows searches, insertions, and deletions in logarithmic time. And it's commonly used in database and file systems, and it's the default implementation of an index when you're creating an index for a SQL table. And I'll go through a formal definition, but it's going to be more helpful in a minute when I actually show you a visualization of how it works. Yeah, so every node has at most, a B tree of order m is a tree satisfying the following properties where m is an integer. Every node has at most m children. So in this example, m is 5. And yeah, if you could imagine this extending down, you couldn't have more than 5 children here, which is obviously different to a binary search tree, which can only have 2 children at most. Every non-leaf node, so a leaf node is a node at the bottom. So these would be leaf nodes as an example, except the root has at most the ceiling of m/2 child nodes, which is 3 in this example. 5/2 joined with 5 ceiling is 3. The root has at least 2 children if it's not a leaf node. So this is the root, obviously, and yeah, has at least 2 children, which you see this satisfies. A non-leaf node with k children contains k-1 keys, and it's kind of easier to see that rather than just look at the definition. So yeah, this is a non-leaf node. Obviously, it's got k children, 3 children, 1, 2, 3, and it contains k-1 keys. So here are the keys 2. And obviously, one of the main differences here between this and a binary search tree is that each node can have multiple keys. That wasn't really obvious. And the last part of this definition is all leaves appear in the same level and can store keys as well as pointers to nodes, but the nodes carry no information. So essentially the child nodes, you could imagine we'd have some sort of empty child nodes here if we wanted to. It doesn't necessarily affect the definition, but they carry no information. So yeah, I won't go through the implementation because it's very long, but this is just an example or kind of visualization. It's a lot more complicated than the binary search tree implementation that was only a few lines. So I'm going to give a quick demonstration of how a B tree works. So imagining the binary search tree, if I entered data as 1, 2, 3, 4, 5, 6, 7, say like that, then it would be just like the example we saw where there would be a 1 and then a 2 on the right and then a 3 on the right and then a 4 and so on. And it would just be going diagonally down and very inefficient. Again, no more efficient than a list, but I'll do exactly the same for a B tree and you can see how it will balance. So there we've added 1, now 2, and I'm just going to quickly rattle through adding numbers up to maybe 10. There you can see it's adding the nodes in and balancing as it goes, or the values into the nodes, sorry, and balancing as it goes. 7, and there we go. It's split up into 3 levels, 8, 9, and then 10. Lastly, and again, you can see it's a very efficient structure because if we want to find a given value, we have to search through no more than 3 nodes because it's got 3 levels. So yeah, obviously then there's also delete, find if anyone wants to have a play around after. Yeah, so there's a bit of a visualization. So now I'm going to show how we use in a real world example a B tree as a SQL index. So by default, in Postgres at least, and as far as I'm aware in most other SQL databases, the create index command creates index using a B tree. So as we just saw, provided the data can be ordered. So obviously you have some types of data that can't necessarily be ordered, but in most examples you have, say, any kind of number or string sort of field can be ordered. And when you've created an index, the index can then be used anytime a query uses one of these essentially comparison operators that requires an ordering. So I'll give an example now. So I've created this table here called users. Created this table here, users, where we've got an ID field, we've got a name field, and an email field. ID is just an integer, and name and emails are strings. And just to make it easier for myself to create a load of data, I just had the surnames as random as integers essentially, just so I could generate a load of data. And you can see here there's 20 million rows, and I just wanted a fair bit of data so you could kind of compare the speed efficiencies that you get from using an index. So I'm going to start off with just doing a select star from users where ID equals 1,000, say, and now ID is by default indexed, so this should be relatively quick, and there we go, 1.5 milliseconds, so pretty quick, even though we've got 20 million rows of data. Now I'll do a query on name, which again is a string by default in Postgres that's not indexed. So yeah, it should be a lot slower. Select star from users where name equals, and I'm pretty sure there's a user with that name, Mary 1000. select star from users, sorry, where name equals Mary 1000. And there we go. So that one took whatever 600 milliseconds, so over half a second. I should just say, by the way, if you want to turn on this yeah, sort of timing thing at the bottom, then it's just this command \timing. Yeah, which obviously I've done already. So there we can see a lot slower to use data that's not indexed. Now, to create an index on that field, we can use the command create index, and I'm just going to call it name_index, but you can call it whatever, on, and then the table users, and then brackets for the column that you want it on. So yeah, I want to create it on name. So there we go. And when I've tested this before, I think it took about 18 seconds, which is why, again, I was saying it's not created by default. That's one of the reasons why it does add a lot of overhead when you're creating a table. If you want to add an index by default, there 70 seconds, as well as you also have the overhead in terms of just storage, because as I said at the start, it's an extra, it requires extra storage space compared to just having the table on its own. So there we go, we've got an index. Now I'm going to go back to that one, and so again, select star from users where name equals whatever. Just because there's a potential issue of that data now being cached, I'm going to change the name to Roy, and there we go. It's far quicker. So rather than, I mean, what was it before, 600 milliseconds, we've got it down to 0.6 milliseconds, so 1/1000th of the time. And again, comparable to the ID query, actually slightly quicker. Yeah, so that's really useful. And you could imagine, if you've got a I don't know, a backend service, and this could be, users might have to perform, or your application might be performing multiple of these queries for any given request. If you can take this query down from 600 milliseconds to 0.6, that's going to make a really noticeable impact on users. So yeah, so I guess this is kind of why they're so useful. There are some cases where this index doesn't bring a benefit. Let's say we wanted to perform some sort of pattern matching query. So select star from users where name is like, and then obviously throw the percentages in there, and I'll just change this again because there's a potential issue of data being cached and making it seem quicker than it should be. So if I perform a like query, then it's not benefiting from the index. And I mean, you can kind of imagine why. So if I go back to here, yeah, I guess you can see here, here we'd have whatever our name, but if you were just looking for, so again, if you were ordering strings, you'd be ordering, I guess, in the yeah, by the first letter and the second and so on. Now that works if you know what the first letter is, but in this query, we don't know what the first letter is, so we don't necessarily know how to traverse this tree. So here we're just having to go back to a kind of traditional looking through every single row, which again here, 20 million rows, it had to look through 20 million pieces of data. So yeah, so they're not always usable, but when you can use an index, then it is, as hopefully you saw there, it's really a lot quicker and a lot more efficient. So on that kind of point about if you wanted to perform a lookup where you were saying, you're doing some sort of pattern matching or looking for substrings, then is that possible? And the answer is yes. So in a less common index, but still useful, is this index called a trigram index. So you split your words or strings rather into these trigrams, which are just sequences of 3 sequential characters. So this string trigram would become, or split it up in each sequence of 3 characters. So tri, and then rig, and then igr. And there you've got your list of trigrams for this word. The index then contains each possible trigram for each string in your table, along with the IDs of the words, which again comes back to having a pointer or reference back to your original data, which is what the ID is used for. I'll show you an example of this in a second. But just some last points on that. It can be generalized to n-grams for any integer n, although, well, there are some examples, you wouldn't want to use 1 as n, because then you've just literally split the string up into its characters, and that isn't bringing you any benefit. But similarly, you wouldn't necessarily want a really large integer. Let's say we were using, I don't know, 10 as our n, then obviously trigram, we couldn't put that into the index because it doesn't have 10 characters. And yeah, so again, trigram indexes can be used to perform this sort of pattern matching or substring searching queries, unlike B trees. So obviously a limitation for trigrams specifically. And if I said trigrams for when I was talking about n, I meant n-grams. But trigrams specifically cannot be used searching strings of fewer than 3 characters. Yeah, which is probably obvious from here. Here's an example of using a trigram. So let's say we've just got 3 strings in our table: Google Cloud Functions, Google Vision AI, Google Recommendations AI. Then we get this index. So the trigram GOO, obviously capital G, is contained in the 0, first and second string. Again, these are sort of the pointers back to visual data, and so on for all of these trigrams contained in any of the words. And that's kind of an overview of how the index might look like. Obviously, implementation details will be more complex. So if we wanted to execute a query, like I was showing earlier, where we're selecting a field based on this substring, then we'd again separate the words into trigrams, or this word specifically, so CLO, LOU, OUD, look up each trigram and find the words containing all of these trigrams, which again, we'd look here, CLO 0, LOU 0, OUD 0. So the only word containing all of those trigrams is the 0 string, this one here. But we also need to check that just because it contains the trigrams, does it contain the entire word, sorry. And so this string, loud clover, would contain all of these trigrams as one example. And obviously this 0th string does there, Google Cloud Functions. So we know that, and then we could return that. And if you wanted to implement that, which I won't show now, Postgres has a module, PG_TRGM, Postgres trigram, that can be used to create this kind of index. And yeah, that about wraps it up. Are there any questions?
Yeah, I have a question. So in the B tree,
Yeah.
you have these keys in different nodes. And so the way to find a particular key is for example, you look at the root node, then you figure out between which of the keys the key you want lies, and you go to that child.
Yeah.
So that's quite clear for integers. But what about like you created an index for a string, I think, for the name. So how does that work in that case? Do you know?
Yeah. So I think it would be essentially the same kind of thing, except rather than comparing, I guess it's easy to see on numbers how you can compare less than or greater than. But so yeah, this is a good question. So for strings, you would also have your strings entered into this data structure. So in the example of the users table, we had, say, James 1000. So this could be James 1000. This could be Mary 2000, say. And so let's say you wanted to find, I don't know, Roy 1000 or whatever. Then you'd compare Roy to James, and R is greater than J. So you would then move to the right, and then you could compare against this one. And yeah, I guess this isn't something I went into, but yeah, it's good to go over now. So, and then here we said we had Mary, and so R is greater than M. Again, in your kind of, I don't know what the word is, but in kind of dictionary order, R is greater than M. So you would know, okay, I'll traverse down right from this this string Mary, and then here we might have, I don't know, Roy, but with a different number, I don't know, 2000. And if we're looking for Roy 1000, then we know that, well, Roy, and then the space is the same, 2 is greater than 1. So if we're looking for Roy 1000, then we traverse left down there, and then we potentially find, or well, in this example, we then wouldn't find anything, so we'd know the data isn't present. But in a larger tree, then you might have more data. Yeah, hopefully that answers the question.
Yeah, okay.
Tom, for I mean, I guess I'm aware of the benefits that indexing has on querying speed. But one thing this presentation has drawn attention to in my mind is, well, there's a question for me over what the impact of indexing is on insertion and updates of rows.
Yeah.
Do you know, I mean, presumably it's pretty minimal, otherwise, people wouldn't use indexes. But do you know anything in that space? Do you know what the impact is on insertion times?
I don't know, actually. I mean, so if we just look at insertion, so obviously there's two parts to the kind of insertion. So the first one is, let's say you wanted to insert, a number like, I don't know, whatever. Yeah, so let's say you wanted to insert a number here. If we were inserting into a non-index table, then obviously you didn't have to do anything, you just stick it wherever. So there's I mean, if you've got an efficient index, it shouldn't be particularly high. I couldn't give exact numbers, but so the point of the B tree is that you can perform insertions in log of n time. So I guess that would ultimately be it. It's a log of n operation rather than order of one operation, like a constant operation. So yeah, it's a valid question. Again, if you're Facebook and you've got 1 billion users, then it's log of 1 billion, or times some constant, I guess, operation. So yeah, it certainly adds quite a bit of overhead, but I would think that in most cases that would be, or the efficiencies you get from being able to update or read data so much quicker, and obviously update data as well so much more quickly, would outweigh it. But I don't know exact numbers.
No, totally agree. I mean, of course, the benefits are going to outweigh. I guess in my head, I'm interested in, we go away and read a bit as to what minimal impact it does have on insertion speeds.
Yeah, definitely.
Anyway, so I think we're at time there, Tom. So thank you very much. And we shall leave it there. Thank you.
Great, thanks.